All right, in Chapter 5, we move to numerical data for everything. So numerical predictor or explanatory variable. Often in regression we talk about predictor and a response. Response. Okay, there we go. So the idea is that you would have typically, so if we say explanatory or predictor, so let's go with explanatory, and then response. In this case, your data would, look like some x1, x2, x3, x4, x5, a bunch of numerical data, bunch of numbers, and so on. And then the response would be y1, y2, y3 for each of those, y4, y5, and so on. And so a nice visual way to see your data is on a Cartesian coordinate system, and we may see some data that look like that, something like that. Now, what we see with these data is that there appears to be an upward trend like that. And that is, in this particular hypothesis test, that's what we're looking for. And now let's see how this relates to our the previous test. So I'm going to redraw that idea. So suppose I have something like this, and we'll make it very simple. Okay, so Chapter 3, chi-square, those were count data. But notice if I have these numerical data, I can categorize them into high and low, something like that. We'll put a couple more dots in there just to have something. You don't have to, but so with these highs and lows, so here would be low, high, low, high. So these are categories. Now they are ordinal categories in that low does mean something compared to high, but just because it's low to high, is low half of high? Well, not necessarily. You could have these two, you could have a point right next to the line there and right next to the line there, in which case they're almost the same value, but one gets categorized as low and the other high. So they're still categories, but they are ordinal. But now, if we had something like this and we just wanted to categorize as high and low, well, then that's what we would do is we would have something that looks like the stuff we did in Chapter 3 with chi-square, where I could count up how many things are both low. So 1, 2, 3, 4, 5, 6, 7, 8, we'll say 10. Doesn't really matter. And then I look up here in this area with high for the response. Okay, so again, this is response. This is X, and this would be explanatory. And so maybe there are 2 there, and maybe there are 12 here, and maybe 4 there. Well, you see that by gridding off the Cartesian coordinates and counting what's in there, when I look at the chi-square, I think we would all look at this table and say, oh, yeah, definitely looks like there's dependency going on there, right? If I'm in the high row, I would tend to assume the other variable is high. If I'm in the low row, I would tend to assume the other variable is low, or vice versa by column. Now, since this is the explanatory, typically, with the scatter plots and so forth, we're really sort of thinking of the columns here. But, if I know I'm in the low column, I would expect that most of my data would be in the low row. And if I'm in the high column, I would expect most of my data to be in the high row. And so definitely appears to be dependent. But if my data looked more like this, and I were to do that same thing and count, notice that, high, low, so low, high, low, high. Low, high. If I were to count these, I might see something more like 10, 11, 12, 8, something like that. In which case, as I'm looking at this one, I think maybe it's independent, right? Is that, or actually I put the low and high up there usually. It looks like, yeah, if I know I'm in the low column, it's about half and half. If I'm in the high column, well, it's a little more high than low, but, could that have come from just the random sample, that these things really are the same? Sure. It could be that the 12 and 8 is the proper proportion, and the 10 and 11 are just, off a little bit due to random sampling, or of course something in between. But at any rate, probably if I were to run a chi-square test on these data, it would probably show independent. I would get a big p-value. And on the other hand, if I did it on these data up here, it would probably be a small p-value and show dependence. And so it's the same thing here. What we're looking for, notice in the bottom graph, really there's no upward or downward trend in the data, and that's what's causing this kind of answer over here in the table. Here, there is an upward trend, but it could be downward. But there's an upward trend, and that is what's causing stuff to, the way things worked here, that as you look at the data here, you also sort of see that trend of where are the most data. It tends to go in that upward fashion. And so that's the link between Chapter 5 and Chapter 3. Is we're really looking at about the same sort of thing. It's just with categories, I may not be able to have an order. So, it works well going this direction, saying, well, okay, I have these scatter plots. Now let's categorize it in low and high, or low, medium, high, or something like that. Ages, we often do things like infants, toddlers, pre-adolescence, adolescence, adult or young adult maybe, and adult, seniors, that kind of thing. And so those are categories that encompass quite a few numerical values, but they're still categories. And so it's pretty easy going from numerical data to categories. Now, going backward from categories to numerical data, the analogy doesn't always work because, well, if you don't have ordinal data, you don't even know what order to put it in on the scatter plot. It would be arbitrary. But nonetheless, this is the idea, is that we might have data in a count sort of situation, but you can think of those counts as being dots within a Cartesian plot, and it's how many dots I would have in that portion of the Cartesian plane. And so you see, you could get something that definitely has a pattern. Now, you could go with low, medium, and high. And here's the funny thing: the two different tests could actually give you some different results. Oops, I'm trying to do this in thirds. So suppose I had low, medium, high, and low, medium, high, and I had a lot of data here. If 10's a lot, we could call it 100. Not as so much data here, maybe just 20 or so, nothing there, nothing here, and I'll make life easy on myself, and I'll just do something like that. But now here, suppose we have, nothing in there, and maybe 40 here, and 40 there, or something like that. Well, probably if we did a chi-square test on this table, we would find that things are dependent. Now, the funny thing is, and this is where you really have to think about tests and what they tell you, is if I do set up this same thing, with dots, our particular test is going to look for this trend. Well, suppose I've got a whole bunch of dots there, a few more in here, quite a few there, quite a few in here, and some more in there, and a bunch of dots up here. And I don't know what the exact right number would be. I just was making numbers up over here. But it could be that when you try to determine a trend for the data over here, actually, your trend might be straight across, in which case here, our particular test would say they're independent, okay, but it's pretty clear, I think they're not independent. There is a dependency. It matters. If I'm in the low row, I should be guessing, or another way to look, I guess if I'm in the middle column, let's go by columns again. If I'm in the middle column, I should not guess high. Whereas if I'm in the low or high column, I should guess high. So that's a dependency, right? And I'm guessing there would be enough here to get a very low p-value. Now, the problem is our test is going to look for a straight line. And really, what we probably have for a trend here is not a straight line, it's something like that. Well, so, that's where you want to look at your data, you want to plot your data, because, which is, really plotting your data is no different than creating a table like that. It just doesn't give the counts, it just shows where every data item is. And so, for any of these analyses, you really should plot your data, because it could be that our hypothesis test will come back and say, oh yeah, there's no either upward or downward trend in the data as a whole, and therefore we're going to say the data are independent. When actually what we can see is that if we plot the data, well, the problem was there was a downward trend here and an upward trend there, and they kind of canceled each other out when we looked at the data set on the whole. Okay, So there is, quit that. There is an introduction to the linear regression as far as just the big idea of what we're looking for. It's a lot like the chi-squared. And next we'll look at relating our numerical data to the analysis of variance test.